All right, welcome to another deep dive. This time we're cracking open headfirst software architecture.
This one's a beast.
Oh yeah, it's clear that anyone listening to this is serious about software architecture, like really wants to get good at it.
Absolutely.
So to kick things off, how about we start with something everyone gets, like building a house?
Love it. Most folks won't think about the architecture of their homes, but it's what makes them livable, safe, adaptable, just like in software,
Right,
actually.
so walk me through this.
Well, imagine building a house, right? But without a blueprint.
Uh-oh,
You might end up with like rooms that don't connect, plumbing that goes nowhere, maybe a roof that can't handle the snow. Total chaos.
a DIY disaster for sure. So how does that translate to software? What happens when we don't think about architecture?
It's the same kind of chaos. You get software that's fragile, impossible to scale, a nightmare to maintain. Ever used an app that's constantly crashing or slow as molasses?
Ugh, all the time. I'm looking at your airline booking app.
That's probably bad architecture at work. It's like the app was built one room at a time with zero overall plan.
Okay, yeah, the stakes are pretty clear. So where do we even begin? How do we avoid building a software shack instead of something well architected?
Just like a house needs that blueprint, software needs a well-defined architecture. And this book breaks it down into four, let's call them dimensions. These are the cornerstones of any good system.
4 dimensions, huh? Okay, lay it on me. What are they?
First up, we've got architectural characteristics. Think of these as like the qualities you want in your house. Do you need it to be energy efficient, earthquake resistant, soundproof for those late night jam sessions?
So it's about deciding what's important for the software, right? Like how fast it needs to be, how secure, how easily it can handle like a ton of users.
Bingo. Just like you wouldn't build a beach house the same way you'd build a mountain cabin, you got to choose the right characteristics for your software. It all depends on its purpose, its environment.
Gotcha. What's the next dimension?
That'd be architectural decisions. These are the big, impactful choices. Imagine choosing the foundation of your house, the materials you'll use, open floor plan versus, something more traditional.
So decisions like what programming language to use, what kind of database, cloud versus on-premise, those sorts of things.
Exactly. These are crucial because they affect everything else down the line. You don't want to be redoing your foundation once the house is built, right?
Right, right. Makes sense. 2 down, 2 to go. What's number 3?
That would be logical components. Now, these are the building blocks of your system, the parts that actually do the work. Think of them like the rooms in your house: kitchen, living room, bathroom, each with its own purpose.
So in like a social media app, you might have components for user profiles, posting updates, managing friends, showing the news feed, that sort of thing.
You got it. And just like you want boundaries between rooms in your house, you want clear boundaries between your software components. Makes the system way easier to understand, maintain, and grow over time.
Okay, I'm following you. Last but not least, the 4th dimension.
This is architectural style. Think of it as the overall design of your house. Are we talking Victorian mansion, minimalist loft, rustic farmhouse? Each style has its own vibes, its own pros and cons.
So different software systems have different styles too.
Absolutely. Just like you wouldn't build a skyscraper the same way you'd build a tiny house, you got to pick the right architectural style based on the size, complexity, and of course, the requirements of your software.
Okay, I see the 4 dimensions now. They're starting to paint a clearer picture for me. But how does this connect back to me at the listener? Why should someone who's not, like, building the software care about any of this?
That's a great question. It all comes down to this. Good architecture leads to better software. For everyone, think about the apps and websites you use every day. Which ones are a joy to use and which ones make you want to pull your hair out?
Oh, don't even get me started on that online banking app.
Chances are the ones that drive you crazy have some architectural issues under the hood. Maybe they're slow, unreliable, constantly crashing. That's because they weren't designed with those entities in mind, the ones we just talked about.
So good architecture is like the invisible force that makes software work well, intuitively, reliably. It's the difference between the apps we love and the ones we hate.
Exactly. And even if you're not a developer, understanding these basics helps you ask better questions, make smarter decisions about the software you use at work, really advocate for better stuff.
Okay, I'm getting the big picture, but let's dig into those architectural characteristics a bit more. The book mentions they can be tricky to pin down. Why is that?
Well, for one thing, there are just so many. Performance, scalability, security, usability, maintainability. It's like trying to build a house that's perfect in every way. Just not realistic.
Right, because you have to make choices, right? Prioritize some things over others. Security over speed, maybe? Or usability over cost?
Exactly, and that's where the problem domain comes in. Understanding the core problem your software is trying to solve. What are the user's needs? The business goals? What are the constraints?
So it's about defining the purpose of the software before you get lost in all the technical details.
Exactly. Once you've got a handle on the problem domain, you can start picking out the most critical characteristics. It's like figuring out if you need a cozy cottage or a spacious mansion, you know?
Okay, that analogy makes sense, but how do you actually go about identifying those characteristics? Do you just lock yourself in a room with a whiteboard and, like, brainstorm every possible scenario?
Well, the book suggests a more structured approach. It's not just about the problem domain, but also environmental awareness, understanding the context where your software will live.
So things like the company culture, their tech infrastructure, maybe even industry regulations, those sorts of things.
Precisely. A fast-growing startup might prioritize speed to market, while a big, established company might focus more on stability and security.
Yeah, because different organizations have different priorities, different needs.
Exactly. And finally, there's this idea of holistic domain knowledge, drawing on your experience, understanding of best practices, even your intuition, to spot those crucial characteristics that might not be like written down anywhere.
So using your judgment to anticipate problems and make smarter design choices?
Bingo. The book gives this great example about a university class registration system. If you only focus on the technical stuff, you might assume students will register evenly throughout the period, right?
Yeah, that seems logical.
But anyone who's been to college knows that students procrastinate, so a good system needs to be ready for that last-minute surge.
Oh, yeah, good point. So that's where that holistic domain knowledge comes in.
Exactly. It's about anticipating those real-world scenarios that can make or break your system.
Okay, so we've looked at the problem domain, the environment, and our own knowledge. We've got a good grasp of those critical characteristics. What's next? Do we just jump into coding now?
Not so fast. Remember those logical components. They're the functional building blocks of your system. Defining them properly is key for creating a well-structured, maintainable piece of software.
So we need to figure out what those components are and how they'll work together before we write a single line of code.
Exactly. It's like planning the layout with your house. You got to decide where each room will go and how they'll connect. And the book has some strategies for defining those components well.
Okay, I'm all ears. How do we go from that big picture idea to those detailed building blocks?
The book suggests two main approaches, the workflow approach and the actor-action approach. Workflow focuses on, well, mapping out the steps a user takes to do something in the system.
So for an e-commerce site, that might be browsing products, adding stuff to the cart, entering payment info, confirming the order.
Exactly. Each of those steps could be a separate logical component, each one responsible for handling a specific part of the interaction.
Okay, I can see that. What about the actor-action approach?
That one's all about identifying the different types of users, or actors, who will interact with the system, then figuring out what actions each one needs to be able to do.
So in like a social media app, you might have regular users, advertisers, maybe admins, each one with their own set of actions.
Exactly, and those actions get grouped into components based on how they relate to each other.
Right, I'm starting to see how this helps break down a complex system into smaller pieces. But is there anything we should watch out for when defining these components?
Absolutely. The book talks about the entity trap. This is where you name components after, well, just the data in your system, like user manager or product catalog.
And what's wrong with that? Those sound like pretty logical components to me.
The problem is those names are too broad. You end up with these bloated components that try to do too much, and they become really hard to understand and maintain.
It's like having a room in your house labeled stuff. Doesn't tell you much about what's actually inside.
Right. We want our components to have clear, specific roles, just like the rooms in a well-designed house.
Got it. So we've identified our initial set of components. What's next?
Well, the book lays out a four-step process for refining that logical architecture, and we'll dive into that in the next part of our deep dive.
Sounds good to me. I'm ready to get into the nitty-gritty of these components. But before we do, maybe our listeners can take a minute to think about a software system they use a lot. What are the key features? Can you imagine breaking those down into components?
It's a great way to start thinking like a software architect.
We'll pick back up with those logical components in the next part of the deep dive. Until then, happy architecting. Welcome back to the deep dive. Last time we were talking about those logical components, the building blocks of a software system.
Right, and how to, break things down from that big picture idea into more manageable chunks.
Exactly. We were just getting to that four-step process the book lays out for creating a solid logical architecture.
Yep, and remember, we're using that fictional adventurous auction system as our example. So step one is to assign requirements to those components.
Okay, so we've got our initial components sketched out, right? How do we make sure they can actually handle the demands of the system? And like that everything stays organized. This is where it feels like things could get really messy.
It's true. Just throwing requirements at components without thinking is a recipe for disaster. That's where step two comes in, analyzing roles and responsibilities.
So it's not just enough to say, this component handles user authentication. We need to like really dig into the details.
Absolutely. What actions are involved? What data does it need? How does it talk to other components? All of that.
It's like figuring out not just the what of a room, but the how, how it functions, how it connects to other rooms, what are its limits.
The book uses the term cohesion to describe how well-focused a component's responsibilities are. A highly cohesive component is like a well-organized kitchen. Everything has its place.
And a poorly cohesive component. That's like the junk drawer we all have, where everything's just rammed in randomly.
Exactly. High cohesion makes components easier to understand, test, and maintain. Crucial for a robust system.
Cohesion. Got it. What's the third step?
That's analyzing component relationships. We look at how those components interact, whether those interactions are, helping or hurting our architectural goals.
Right, because it's not enough to just have good components in isolation. They need to work well together, too.
Exactly. Think about the layout of your house. You wouldn't want to have to walk through the kitchen every time you need to use the bathroom, right?
Yeah, that would be awkward. So how do we avoid those kinds of weird, tangled relationships in our software?
That's where the idea of coupling comes in. Coupling is about how much one component depends on another. Too much coupling, and your system becomes this tightly interwoven mess. Change one thing, and you break everything.
Like a domino effect. One little change can topple the whole structure.
The book calls this the big ball of mud anti-pattern. It's a nightmare scenario, every component tangled up with every other component.
Okay, yeah, I'm definitely getting big ball of mud vibes from that online banking app we talked about earlier. So how do we avoid creating that kind of mess?
One key principle is to minimize unnecessary coupling. Make those components as independent as possible so changes in one don't break the others.
Like having modular furniture, you can rearrange things without having to take the whole room apart.
Exactly. And one way to do this is by following the law of Demeter. It says a component should only talk to its immediate neighbors, not components further away.
So if component A needs data from component C, it shouldn't go directly there. It should go through component B, which is already connected to component C.
Right, like borrowing a tool from your neighbor. You wouldn't go knocking on doors 3 streets over if your next-door neighbor already has what you need.
Great analogy. But does minimizing coupling ever have downsides? It seems like it's always presented as a good thing.
You raise a good point, and it shows how software architecture is all about trade-offs, right? Too much decoupling, and it can become hard to understand the system as a piece.
It's like having a team where everyone stays in their lane, but no one knows what the other teams are doing. You get communication breakdowns, things fall apart.
Right, you need balance. Sometimes a bit of coupling is actually good, for the system to work smoothly. It's about making those choices consciously and documenting them.
Okay, so analyzing relationships and managing coupling. Got it. What's the final step in refining this logical architecture?
That's analyzing those architectural characteristics we talked about earlier: performance, scalability, security, all those non-functional requirements.
The ilities that make the system actually work well in the real world.
Exactly. We go back to our components and their relationships and ask, does this design actually support those critical characteristics?
So if scalability is important, we got to make sure our components can handle lots of traffic without falling apart. And if security is key, we got to make sure they're not leaking data.
Exactly. And sometimes you'll find you need to refine components, decouple things, maybe even rethink some earlier decisions.
It's like realizing your house needs more electrical circuits or better insulation to save energy.
Precisely. It's an iterative process. Analyzing characteristics ensures our architecture is really fit for purpose.
Okay, I'm seeing how those 4 steps lead to a really thoughtful design process. But once we've gone through all this, how do we actually record those decisions, make sure everyone's on the same page?
That's a great question. Architectural decisions are one of those 4 key dimensions we discussed, and capturing them is crucial.
Right, because if we don't, we might end up having the same debates and analysis later on, or even forget why we made a certain choice in the first place.
That's where architectural decision records, or ADRs, come in. ADRs are like little case studies that capture not just the decision, but the context, the reasoning, the potential consequences.
So it's not just we chose this database, it's here's why we chose it, what factors we considered, what trade-offs we made.
And the book captures this beautifully with the second law of software architecture. Why is more important than how. Understanding the why helps us make better decisions in the future, even as things change.
Okay, I can see the value in that. But what actually goes into an ADR? Is there a specific format?
The book suggests a 7-section template. We'll get into the details in the next part, but first let me ask you, listener, have you ever worked on a project where a key decision wasn't documented and it came back to bite you later?
Oof, I bet a lot of people have been there. It definitely highlights how important it is to capture those decisions.
Absolutely. We'll delve into a world of ADRs in the next part of the deep dive.
Welcome back to the deep dive. We've been getting deep into the nuts and bolts of software architecture, those all-important abilities, crafting those logical components.
Right, building those solid foundations.
Exactly. But now it's time to zoom out a bit. Look at the big picture. Talk about those architectural styles that shape the whole system.
It's like choosing the blueprint for your house. Victorian, modern, sprawling ranch. Each one's got its own, character, its own trade-offs.
Okay, yeah, I get the analogy. So, what are some of the popular styles in the software world? And how do we know which one's the right fit for a project?
Well, the book dives into 5 common ones: layered architecture, microservices, space-based architecture, event-driven architecture, and then pipeline architecture.
5. Wow. Okay, let's take them one by one. Starting with layered architecture. What's the basic idea there?
Layered architecture is all about, well, layers. You organize your system into these distinct horizontal layers, each with its own specific job. Think of it like, well, a layer cake.
Okay, I can picture that. So you might have a presentation layer at the top for the user interface, then a business logic layer in the middle, and a data access layer at the bottom talking to the databases.
Bingo. And the key here is each layer only talks to the ones right above and below it. It's like a chain of command.
Keeps things organized, I guess. What are the advantages of going with a layered architecture?
Well, for one, it's pretty straightforward to understand, especially for smaller applications. Good for teams who are, newer to architecture or systems with simple requirements.
Like building a house with a traditional floor plan. Easy to find your way around.
Exactly. Layered architecture is also good for code reusability. Since each layer has a specific job, you can often reuse those components in different parts of the system.
Ah, like prefab building blocks. You can use them to make different parts of the house.
Precisely. But like any style, it has its limitations.
Yeah, I was just thinking, it seems like it could get pretty rigid. What happens when you need to make changes or add new features?
That's a great point, and that's one of the big downsides. It can become what we call monolithic, hard to scale as the system grows.
Monolithic. So the opposite of that modular decoupled approach we talked about before.
Exactly. You add more features, more complexity, those layers get all tangled up. It's hard to change one thing without breaking something else.
Yikes. Like trying to renovate a house where all the walls are load-bearing. Move one thing and the whole structure could collapse.
That's a good analogy. And that's where microservices architecture comes in. It's all about breaking down that monolith into smaller, independent services.
Microservices. So instead of one big cake, we've got a bunch of mini cupcakes.
Ha, I like that. Each microservice is like its own little world. It represents one specific business function, and it can be developed, deployed, scaled, all on its own.
So for our e-commerce example, we might have different microservices for managing products, handling orders, processing payments, all separate.
Exactly. And they talk to each other through like these clear APIs. Makes for a flexible and scalable system.
Sounds very modern, very agile. What are the benefits there?
Well, it lets teams work faster and more independently. Since each microservice is its own thing, teams can work in parallel, without stepping on each other's toes.
Like having different construction crews working on different parts of the house at the same time.
Precisely. And it makes scaling easier, too. If one service is getting slammed, you can just scale up that one without affecting the rest of the system.
Like adding more checkout lanes to a busy store, but you don't have to rebuild the whole building?
Exactly. Of course, microservices have their own challenges, too.
I was just thinking that. Managing all those separate services sounds complicated.
Oh, it can be. You need the right tools and processes to, keep track of everything. Monitoring, deployment, troubleshooting, it all gets more complex.
Like managing a whole fleet of delivery trucks instead of just one. More moving parts, more chances for something to go wrong.
Exactly. That's why microservices are usually a better fit for bigger, more complex applications where the benefits outweigh the added overhead.
Okay, so layered architecture, microservices. 2 very different approaches. What about those other 3 styles? Space-based, event-driven, pipeline. What makes them unique?
Well, space-based architecture is all about distributing your data and processing across multiple nodes. Often in a cloud environment, it's great for handling huge amounts of data or traffic like social media platforms or online games.
So instead of one central warehouse for your inventory, you've got multiple warehouses spread out.
Exactly. It improves performance, scalability, and makes the system more resilient. Then there's event-driven architecture. It's all about reacting to events, changes in state, very dynamic, very asynchronous, good for real-time systems.
Like a security system, maybe. It detects motion, and boom, triggers an alarm.
Precisely. And lastly, pipeline architecture. It's like an assembly line for data. You process the data through a series of stages, each one doing its own specific thing.
Okay, so like a factory. Each station performs a specific operation on the product as it moves down the line.
Exactly. Breaking down the process into these stages makes it super efficient.
Wow, we've covered a lot of ground here. 5 different styles, each with its own pros and cons. It's clear there's no magic bullet when it comes to software architecture.
You said it. The right choice depends on so many things. The specific requirements of your app, the size of your team, their experience.
And it all comes back to those arities, right? We got to choose a style that supports those and, lets our system actually thrive.
Absolutely. Software architecture is about making informed decisions, knowing those trade-offs, creating a blueprint for a system that can grow and adapt.
It's been fascinating exploring all of this. Really opened my eyes to how much it goes into building a good system.
And remember, this is just the beginning. There's so much more to learn about software architecture. Keep experimenting, stay curious, always keep striving for that perfect balance between form and function.
Well said. And that's a wrap on this deep dive into software architecture. Thanks for joining us, everyone, and until next time, happy architecting.